Hey everybody, Mike here. I'm driving in my car. You know, my car is pretty cool because it has a rate meter. I don't know if you got one, but it's like right there. See? Right now it says I'm going like 20. There it is, right there. Kilometers divided by hours. And then if I push on this pedal makes me go at a faster rate. And if I go at a faster rate, I'll cut down on my time. And I'm already late for Turnip Fest. So if I double my rate, it'll take me half the time to get to the Turnip Festival. So let's go talk about rates. Because I'm being tailgated by a black and white car. Go around! Just go. He's really tailgating. Now he's flashing lights at me. Show off. Well, hi everybody. Hi, I'm back. It turns out I didn't get to go to the Turnip Festival. I didn't know this, but you can actually get pulled over for driving at a too slow of a rate, and you're not allowed to keep your blinker on the whole time. But I'm back and everything's good. Here we're going to talk about rates of reactions. Sometimes they call this kinetics. Most of the time they call this field kinetics. Sometimes they get fancy and call it dynamics. But the bottom line is we want to know what speed of a reaction there is, and the way we measure any rate in society, like I said before, some level of progress over time. So in my car, it's got the rate meter, kilometers per hour. That's the one you look at. Makes you feel like you're going faster if you look at that one. And then of course, you know, hey, you interview for a job and then you answer blah 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 yada yada, but what you're always wondering is, what's my dollars per hour? Or, you know, the time unit doesn't always have to be the same. It might be dollars per year. So you change the time unit to be what's appropriate. Like, think of how silly it would be if I calculated how many kilometers per second I'm going. We would have no real frame of reference. The numbers would be way too big and clumsy. And so that's a little bit about rate. You will find that in our area, progress is usually in concentration. So big M, moles per liter per time. Moles per liter per second, moles per liter per minute, moles per liter per year, depending on how fast the reaction is, and so on. So we're going to talk about next, what do you do to speed up or slow down a reaction? And I think you can basically boil it down to about 4 things, which we will be talking about for a bunch of lessons here. And so think about that. What are the factors you think you can change if you want to make something that's a chemical reaction speed up? And probably the one that jumps right into your brain is that you say temperature. So, for example, one time when I was a kid, I got in trouble with my mom because I accidentally left the milk out. And at the higher temperature of room temperature, the milk spoiled. So the process sped up, and then my mom said, I could have done better. Yeah. So anyhow, that's one of those things. If we increase the temperature, the rate will go up. Another is if we increase the concentration. And that comes in lots of different forms, but you know, if we increase the number of moles per liter, molecules sometimes have to bump into each other, and then you can affect the rate that way. Or you might say, hey, pressure, you know, the pressure, I'll increase the pressure. Well, pressure is really concentration. If you go, remember good old PV equals nRT, if you go and solve for N over V, it's got a P over on the other side of the equal sign. So pressure and concentration are really kind of talking the same language. The other thing is that you can get a helper that makes the reaction go faster, and that would be called a catalyst. And finally, another thing is we could change the surface area. So you get a big old Sunday newspaper and you say, I'm going to burn this. And not that you'd do that kind of, well, maybe nowadays you would. But, you know, you go, I'm going to burn this. Well, you know, it would burn it much faster if you took every single page and crumpled it up and then lit that on fire than if you took the, you know, folded up newspaper with no exposure to the air. And so surface area is why in your automobile, unless of course you got an electric automobile, but you are not really burning the liquid gasoline, you're burning finely divided droplets of gasoline, which is really sort of a vapor, and that explodes, but the liquid burns much slower. So those are the things that you can do to affect the rate of change of a chemical reaction. So now what we're going to do, we're going to take it easy with you folks today in terms of numbers, but I'll tell you right now, the study of kinetics is a mostly numbers game. Let's talk about rates of reactions and how we express them next. Oh boy, a chemical reaction. You're no strangers to that. And so the only thing is you might realize that the way I have it written there is perverse because the chemical reaction is not balanced. So that we need a quick balancing job here. We need to stick a coefficient of 2 right there. So there's going to be equal number of oxygens, hydrogens on both sides. 4 hydrogens, 4 hydrogens. 2 times 2 is 4 hydrogens, oxygens. 2 oxygen. There you go. Now, here's something that might be a bit foreign to you. We're going to talk about what if you had just H2O2, by the way, this is hydrogen peroxide. You get it as a solution that's 3% in the drugstore or whatnot. But we have it in 30%, and I suppose it could be even purified. But right there, we're gonna call that point. We're gonna call that, okay, here's some things to save you time. The way we talk about concentration is if we say it's in molarity, we make brackets. H2O2. In brackets, that means moles per liter. And so just so you know, what we do also is if it is the initial concentration, that's what we call the concentration at time 0. Let's even write that out. This is initial concentration. So H2O2 in brackets with a little sub-zero. What's going to happen is you go put that in a container. Now when you get it at the drugstore, it's in a brown container because the sun will actually make this process happen. And I believe they even put maybe some stabilizers in it when you get it from the drugstore. But over a length of time, that amount of H2O2 will decay. When you pour it out on things, you will see it's got bubbles in it. And so even if you left it alone to nothing, it would decay. And so the way that looks a lot of times in a chemical reaction is like this. It doesn't just blink an eye and then it's over. It kind of goes like a curve. And then the bad thing is it'll go to 0. But the kind of bad thing about that is that we now can't use simple mathematics to talk about this. We've got to start talking about logarithms, but we're not going to do that today. So that's kind of what would happen here. And then the water would increase. So the rate of change here is negative, even when it starts slowing down. Now, by the way, why is it slowing down like that? That's because as the number of reactant molecules disappear, there's a bunch of different ways a couple main ways the story of this happens, but either a molecule needs to hit a molecule of itself, or it just decomposes. We'll talk about all that later, but the bottom line is there's less reactant molecules around, and so the rate of the reaction slows. Now, and that's why the curve happens. Curve's real steep, and then it kind of narrows out, and then eventually goes to zero on its own terms. The water, so this is H2O2. That's what that symbolizes. What would the water be like? Well, every 2 molecules of this that disappear, 2 molecules of that up here, and so it would be like the mirror image. And so this would be your water. I'm putting it in brackets. We'd say that's the concentration of water. Now think about this with me, folks. What would the concentration of O2 look like? Well, for every 2 molecules of water you make 1 molecule of oxygen. So everywhere on this, the rate of production would be half that of water. And so, you know, if I could draw this, you know, the change everywhere, this would be O2. And now, what are we talking about when we're talking about the rate of something? When we're talking about the rate of something, we are talking about the change in concentration over change in time. So if I just pick any time, there, who knows how many minutes that is, or seconds, or femtoseconds, or years. That's a slope. That's a slope. And actually what we find out is that if I drew this correctly, you know, 2 of these slopes would be the same, but one the negative of the other. And one of the slopes would be half of the other. And so what we usually do is we want to talk about the rate of the reaction as if it's one whole sort of entity. And so what you really do is if you wanted to say, how am I going to speed this up or slow this down, or what's the function that this curve adheres to, well, the bottom line, folks, what you would do is you'd need, you know, some mathematics to talk about that, but you would really measure what's easiest. Maybe something has a color, maybe something conducts electricity, and then you'd monitor that. But, you know, what we could do is we could say the rate of this reaction is change in concentration over change in time. And it's easier to talk about the thing that has a coefficient of 1. It would be the change, that's a delta, so change in the concentration of O2 over change in T. We'll call time T. All right, that would be one way to express that. If we knew what the slope was, we could say that's 0.1 moles per liter per minute. And we could then say, all right, and then what is it over here? You know, it slows down to, you know, 0.05 or something like that. So this is just, today we're just talking about the language of kinetics and how we're going to express these things. By the way, this would be 1/2 the change in concentration of H2O over the change in time. Notice here, this is back to this, back to Gen Chem 1. For every plus x of this you make plus 2x. And you would then see a disappearance of minus 2x. And so this would actually be equal to minus 1/2 of the change in H2O2 over change in time. And this would all result in the same number. So, you know, if you did the negative 1/2 and the 1/2, and so we'll just stick some numbers in here and say how we would solve for this. We would say if the rate of concentration of O2 is, and I'm just going to make some numbers up, all right? 0.250 moles per liter per minute. Then I would know that it would be double that rate for the H2O. So that would mean concentration of H2O. And I'm not reading this thing's mind. I'm looking at the equation and seeing that there is a coefficient of 2 there. For every O2 I make 2 H2Os. That would be double that, and that would be 0.500 moles per liter per minute. What would the concentration of H2O2 be doing? Well, it would be going down. But it would be going down at the same rate that the concentration of H2O is going up because of the coefficients. This would be minus 0.500 moles per liter per minute. So sometimes you can get away without using the negative signs. If they let you off easy in a homework problem or something like that, what they'll say is the rate of disappearance or the rate of appearance. Now you don't have to worry about negatives and positives, and therefore it's a magnitude. So we could say the rate of disappearance is 0.500 moles per liter, and don't worry about the negative because you can't have negative stuff disappear. And so if you see a word like rate of appearance, rate of disappearance, it's now not necessary to worry about positives and negatives. But if they just say the rate of change, then it could be positive or negative. Is it going up or down? And do you see the wonderful opportunity here? And I'm being completely sarcastic. The wonderful opportunity to bring more kinds of mathematical techniques to it, because if you are taking calculus, first of all, I feel sorry for you. I took 4 of them. I took them all. And this is kind of like what we call a derivative. Change over change in time. And so we're not going to do that to you because calculus is not required in Gen Chem 2. However, go and brush yourself up on logarithms because we're going to have to express curves with logs, natural logs, base 10 logs. That's what's coming up, not quite next time, but in the future. Folks, that is an intro to dynamics, kinetics, whatever you want to call it. And drive safely. Don't do like I did. I had to be cute and use my camera in the car, and that's not a very good example, and I'm sorry for that. And there is no turnip festival. I just made it up, but I wish there was, because I love me some turnips. Okay, I'm talking too much, and now's the time for me to stop. I need my rate of word production to go to 0. And have a good one, folks. Enjoy your day. See you next time.